Hi everybody. So in today's lecture I'd like to talk to you about conservation of momentum, and this accompanies sections 10 and 11 in chapter 3 of Matter and Interactions. So conservation of momentum is most often used in introductory physics courses when you're doing collision type problems. And so in collision problems you're going to have two or more particles, and you're going to define them as what we call an isolated system. Okay? Now what that means is that the particles interact with each other, but you're ignoring interactions with things that might be outside of that system. So if this happens, if you have two or more particles in an isolated system, then the total momentum of the system remains constant, because the sum of any external forces is going to be zero. This comes from Newton's second law. Remember that Newton's second law says that the sum of all the forces on an object is equal to the change of momentum divided by the change in time. Okay? So if the sum of all the external forces is zero, then that sum of all forces, which equals to delta P over delta T, is equal to zero. So that means that there is no delta P, right, in a certain time interval. And so that means that the initial momentum of the system has to equal to the final momentum of the system, and that implies conservation. Okay? Now it's important to understand that that means that the momentum of the system is conserved, not the momentum of an individual particle. Case in point, let's say that you have particle 1 coming in, moving in on particle 2. Particle 1 moves in, boom, transfers momentum to particle 2. Particle 1 then sits still and particle 2 continues on. Well, obviously the momentum of particle 1 isn't conserved, right? Because it went from moving to sitting still. It's therefore just transferred its momentum to particle 2, and you're defining particle 1 and particle 2 as being in the system, okay? So another way of saying it is that, of course, it's conservation, so that means initial equals final. And that's the case whether you're talking about conservation of energy, conservation of angular momentum, whatever. It means conservation of whatever you're talking about means that the initial equals to the final after the system goes through some process or change. Okay, so you can express it mathematically in a bunch of different ways. You can say that the total momentum of the system, which might be the sum of the momentum of all the constituents, is equal to some constant, okay? You could also say that P1 initial plus P2 initial equals P1 final plus P2 final. And of course, if you had more than two particles, you'd just continue on with that way of expressing it. Now you can also write it out in terms of the components of the momentum. So for example, what conservation of momentum means is that the x components are conserved, the y components are conserved, and the z components are conserved, okay? Because the directions are independent from one another. So you could express it as P1 initial, or P initial in the x is equal to P final in the x, and then separately write a set of equations for P initial in the y equals P final in the y, etc. Okay? Now, in a lot of problems in introductory physics courses, you might have just 2 or 3 particles, but of course, theoretically, the conservation of momentum can be applied to systems with any number of particles. All right? I think it's best to just do some example problems so that you get a conception of what's going on here. So here's example problem number 1. This is a pretty straightforward and simple one, and you can tell that my artist skills are pretty limited, but here's some stick figures, okay? Okay, so we have a man of mass 70 kilograms and a boy of mass 35 kilograms, and they're standing together on a smooth ice surface. Anytime you see the keyword smooth in physics problems or slick, it often means that you can neglect friction, right, in introductory textbooks. So you can assume that. So we're going to neglect friction. If they push each other apart, making the man move at 0.3 meters per second relative to the ice, then how far apart are they after 5 seconds? Okay, so the idea here is that the man and the boy are standing next to each other. They're on skates on ice or whatever. They give each other a push. The man goes one way, and to conserve momentum, that of course means that the boy has to go the opposite direction. Okay? So, first step in any good physics problems is, if you can, draw yourself a picture. Given my limited artistic skills, I've done that here. Also, you write down your knowns and what you need, okay? So I've done that here on this sheet. So here's my initial condition. The knowns associated with this initial condition are the initial velocity of the man and the boy, which I have written here as VIM and VIB. Those are both 0. They're at rest, in other words, okay? Now, here we have the final condition, and this one is the man and the boy moving apart from one another, okay? Now, this is a one-dimensional problem. I'm going to call the motion along the x-axis the dimension of choice here. And so right now what I'm just doing is I'm writing about the x components of the final velocity of the man and the final velocity of the boy, okay? So the final velocity of the man is the final speed of the man is 0.3 meters per second. That should be a 0.3, sorry for the typo. Okay, so that's 0.3 meters per second. And I chose the direction of the man as the negative x direction. And so that means that the boy will move in the positive x direction, okay? Now we don't know what the final velocity of the boy is, so I just put a question mark to indicate that. And the other thing that the problem's asking about is the distance that the man and boy are apart after a time of 5 seconds. So I've written that as d is equal to question mark, okay? We don't know what that is. Other knowns that we can list here, shown on the slide, the man's mass is 70 kilograms, and the boy's mass is 35 kilograms, and the time elapsed that we're worried about here is 5 seconds. Okay, so those are our knowns. Okay, so momentum's conserved because there's no external forces. So since they both start out at rest, the initial momentum of the system is 0. But momentum's conserved, which means that P initial is equal to P final. So that means that the P final also has to be 0. The man and the boy make up the system, so the final momentum of the man and the boy in the x direction, of course here is what I'm talking about, must add to be 0. So I have 0 is equal to P final, which is equal to 70 kilograms times minus 0.3 meters per second. That's the final velocity of the man, right? So this is the final momentum of the man, 70 times minus 0.3. And now we've got to add in the momentum of the other particle, which is the boy. So that's going to be m times v final boy, which is 35 kilograms times v final boy. So my equation looks like 0 is equal to 70 times negative 0.3 plus 35 times v final boy. All right? And this is all in the x direction. So now I can solve for v final of the boy just by rearranging that equation and solving algebraically. So that means that 70 kilograms times 0.3 meters per second moves to the left-hand side of the equation. On the right-hand side, I have 35 kilograms times v final boy. Solving for v final boy by dividing both sides by 35 kilograms, I end up with v final of the boy is 0.6 meters per second. Okay? So we know now what v final of the boy is. We know what v final of the man is. So we will just use our kinematics equations just to solve for the distance in between the man and the boy after 5 seconds. So we have to sum the distance that the man covers in 5 seconds with the distance that the boy travels in 5 seconds. And then that will give us the total distance between the people, d. Okay? Their velocities are constant after they push off, assuming friction is negligible, which we assumed in step number 1, right? So just using the idea that the distance is equal to the speed times the time, here we go. The distance that the man travels would be 0.3 meters per second times 5 seconds. Okay, the acceleration here is 0, right? So that gives me 1.5 meters traveled by the man. The boy has traveled 0.6 meters per second times 5 seconds. That means 3 meters traveled by the boy. And so that makes the total distance in between the man and the boy 3 plus 1.5 meters, or 4.5 meters. Okay? So that's a pretty straightforward example here, pretty straightforward application in one dimension of momentum conservation. So let's kick it up a notch and do a 2D example, okay? So here we have two cars of equal mass approach an intersection. Car 1 is traveling 13 meters per second east, and car 2 is traveling north. They collide in the intersection and stick together, leaving parallel skid marks at 55 degrees north of east. The speed limit is 35 miles per hour. The driver of car 2 claims he was traveling within the speed limit. Is he lying? So this is a little CSI action, isn't it, right? Okay, so I find pictures to be very helpful sometimes in these conservation of momentum problems, as long as the pictures don't get so complicated with so many particles and they stay in 2D. So then I find it easy to draw, okay? So what I've done here is I've made the conventional choice that we make in our Matter and Interactions textbook, which is that the XZ plane is the horizontal plane and that Y is up-down, okay? Now I've chosen my Z-axis to be my north-south axis and my X-axis to be my east-west axis. Excuse me, that was hard to get out. Say that 5 times fast. So plus Z is north and plus X is east. Okay, so that's how I've defined it. So here I show car 1. Now remember, it was traveling at 13 meters per second east. So car 1 is shown here in red, traveling east. So pointing with the velocity vector pointing in the plus X direction. Then car 2 was traveling north. They didn't tell us what car 2's speed was, okay? But car 2 is traveling north. So I've drawn car 2 in blue traveling north. So what's going to happen here, it says in the problem they collide at the intersection and stick together. So since I started off with red and blue, I drew a big purple box to symbolize them sticking together, because red and blue mixed together make purple, right? So I have this purple box. And you don't know its final speed, but you do know that it leaves skid marks at 55 degrees north of east. So I have drawn the final velocity vector of this car sandwich here at 55 degrees north from the east axis. Remember, if it says north of east, then that means you start east and swing north by the amount specified, which here is 55 degrees. Okay, so that's what I've drawn to the best of my ability. Okay, all right, so that's my picture. That helps explain my picture. Now, next step would be to write down your knowns. Okay, so your knowns, of course, P is equal to mv, momentum is equal to mass times velocity. So P1 initial. Now notice that nowhere in the problem does it tell you what the mass of the cars is, but it does say they're the same. Okay, so I have chosen to call the mass of the cars M, because I'm very creative that way. So P1 initial here is MV initial. Okay, so MV1 initial. So car 1 was traveling east at 13 meters per second. So in our vector notation, remember X is the east. So here we have 13 meters per second, comma 0, comma 0, because the velocity vector has no components in the north, south, or up-down directions. So I've just written that out here in our vector notation that's standard. Okay, now car 2, P2 initial, would be the mass of car 2 times the velocity of car 2. All right, now we don't know what the initial velocity of car 2 is. Okay, we don't know that. But we do know that it's to the north, which is the plus Z direction. So I've left the X and the Y components in my vector. Remember, this triangular bracket notation indicates a vector in your Matter and Interactions textbook. So I've left those as 0. And then I've put the north direction here plus Z. I've just labeled it V2 initial. I've left it an unknown. So I don't know what it is, but I'm showing here in my knowns that I know the direction. Okay, and that in itself is very super helpful. Okay, now P final, all right, I don't know the magnitude of the velocity, right? I don't know how fast they were going after they collided, but I do know the direction. Okay, so what I'm going to do is I'm going to call the final speed of the car sandwich V final, okay, because why not? The mass of the thing is now going to be 2m because the cars are stuck together, right, in a little sandwich. So I don't know what the masses of the individual cars are, but I do know that it's twice the mass that I started with. So I call it 2m. And then I've written out my components here. If I look at the trigonometry of the situation, then if I'm trying to find the x component, I would use the cosine of 55 degrees because that's the adjacent side to the right triangle that the final velocity vector hypotenuse makes here. Okay, so it's v final cosine 55 giving me the x component, which leaves sine 55 for the z component. So, and of course it's not jumping off the pavement, so the y component, up down component is 0. So my p final is 2m, v final cosine 55, 0, v final sine 55. Okay? Hopefully that's pretty clear, but if not, just pause the video and stare at it for a few minutes. Okay, so I really need, what the question is asking me for is the speed that car 2 is going. So that's v2 initial here, written in, it's just the component of the velocity vector in the z direction here. So v2 initial, I need to know what that is, okay? So what equations am I going to use to get me there? Well, I'm going to use the only equations that I know to use here, which is momentum conservation. So the form of the equation that I've chosen to express it is the sum of the momenta in the initial is equal to the sum of the final momenta, okay? Vector addition. So that's what I'm going to do, all right? Okay, so I'm going to sum them up. Sum of P initial equals sum of P final. So here we go. M times 13 meters per second, 0, 0, plus M times 0, 0, V2 initial. Those are the two vectors that I'm summing for the initial momenta. And then that equals to the final momenta. Now in this case, I just have one term in my final momenta summation, which is 2M, V final cosine 55, 0, V final sine 55. Okay? All right. Now the masses, I don't know what it is, but I do know that they cancel because the masses appear in every term on both sides of the equation. So I can cancel those out and move the 2 inside my vector if I want to. And when I do that, and then add the vectors, and when I do that on the left-hand side, okay, I end up with a vector of 13 meters per second, 0, V2 initial. Looking at the components, right? You add them component-wise. So for the x, I'm doing 13 plus 0. For the y, I'm doing 0 plus 0. And for the z, I'm doing 0 plus v2i. So that leaves me with the vector shown here on the left-hand side. Now on the right-hand side, I'm going to move the 2 inside. I'm going to multiply everything by 2. And I don't have anything to add because there's just one term. So on the right-hand side, I have 2 v final cosine 55, 0, 2 v final sine 55. Okay? So now I can look at the components. And the individual components I can solve algebraic equations for. So let's look, for example, at the x components of the vector on the left and the vector on the right. The x component of the vector on the left is 13 meters per second, and therefore the x component of the vector on the right has to equal the x component of the vector on the left in order for momentum conservation to be satisfied. So I end up with 13 is equal to 2v final cosine 55. So that means I can algebraically solve for what v final is. V final would be 13 divided by 2 cosine 55. And when I plug that into my calculator, I end up with 11.33 meters per second. So that's how that's what the final speed of my car sandwich is. 11.33 meters per second. Okay? Now I can use that final speed of my car sandwich and solve for V2 initial. Looking at the z components of my initial and my final velocity vectors here, my initial component in the z is v2 initial, and that has to equal the final component of my velocity vector, right? Which is 2v final sine 55. That has to be the case for momentum conservation to be satisfied. So that means that v2 initial is equal to 2vf sine 55. Plugging in for my final speed of 11.33 meters per second, I can solve, right? Plug that into my calculator. And I end up with 18.6 meters per second, okay? Now, after all that, I still haven't quite answered the question, have I? Because the question was, were they speeding, okay? They're trying to find who's at fault here in this crash. So, what we would do then is do a unit conversion from 18 meters per second into miles per hour, which I do here on the next slide. There's 3,600 seconds in 1 hour, okay? And there's 1,600 meters in a mile. So 18.6 meters per second times 3,600 seconds per hour times 1 mile divided by 1,600 meters, that converts it into miles per hour. And what I get is 41.8 miles per hour. So yes, speeding, since the speed limit is 35 miles per hour. Don't tell anyone this, but I don't know, I would consider that not really speeding. Close enough, right? Come on. Okay. All right, so that's pretty much what I wanted to talk about today. Wanted to go over momentum conservation, give you a couple of examples with vector notation to chew on, and if you have any questions about any of that, let me know, and I'll see you in class.